Hello, mathematicians. Now that we've mastered counting the multiples of base 10 digits and used those multiples to construct a multiplication table, let's revisit the patterns and relationships that we've already discovered and see if we can discover some new ones. First, let's talk about how to read the multiplication table. If I want to find 4 times 7, I'm looking for the fourth multiple of 7. So I need to be in the fourth row of the multiplication table and the seventh column. This cell gives me the fourth multiple of 7, which is 4 times 7, and 4 sevens make 28. If I want to find the ninth multiple of 3, I look in the ninth row of the multiplication table and the third column. This cell gives me the ninth multiple of 3, which is 9 times 3, and 9 threes make 27. Where would I find the seventh multiple of 8? The seventh multiple of 8 would be in the seventh row of the multiplication table and the eighth column. The seventh multiple of 8 is 56. So 7 eighths make 56, or 7 times 8 equals 56. Now let's look for some patterns and relationships among the multiples that we've already discovered and see if we can find them in the multiplication table. Pause the video and make a list of all of the patterns and relationships you can find in this multiplication table. Since we've been talking about multiples of base 10 digits, I'm going to gray out the multiples of 10 for now. So the first thing that I looked for was 10. Where does 10 appear in this multiplication table? Ten appears here, the 10th multiple of 1, here, the 5th multiple of 2, and here, the second multiple of 5. So there are 3 tens in this multiplication table. And that makes sense because we already said that 10 is a multiple of 1, 2, and 5 because 10 can be evenly divided into 1, 2, and 5 groups. So that's one familiar pattern that we've found in this multiplication table. We already said that the 5th multiple of 2 is 10. But I also noticed that the 5th multiple of 4 is 20, and that's the first multiple of 4, that's a 10. The 5th multiple of 6 is 30, and that's the first multiple of 6, that's a 10. The 5th multiple of 8 is 40, and that's the first multiple of 8, that's a 10. So I can see that 5 times any even digit makes a 10. The 5th multiple of any even digit will be a 10. And those 10s will be the first multiples of those digits that are 10s. Actually, 5 times any even number is always a 10. And there's a very good reason for that, which I'm going to challenge you to figure out. What about the odd digits? What do you notice about the first tens that are multiples of odd digits? We already said that the second multiple of 5 is 10, and the 10th multiple of 1 is 10. But how about 3, 7, and 9? The first multiple of 3, that's a 10, is the 10th multiple. So when we're counting by 3, we don't get to a 10 until 10 times 3. The first multiple of 7, that's a 10, is 70. So when we're counting by 7, we don't get to a 10 until 10 times 7, the 10th multiple. The first multiple of 9, that's a 10, is 90, and that's also the 10th multiple of 9. So, except for 5, which is exactly half of 10, all of the other odd digits do not get to a 10 until the 10th multiple. 10 times 1, 10 times 3, 10 times 7, 10 times 9. Okay, mathematicians, now it's time to talk about a new pattern in the multiplication table that is very, very important. I wonder if you've figured out what it is yet. Pause the video. If you're working with someone, explain to them what you think it is. If you're not, you can pretend that you're explaining to me. Did you figure it out? Well, here's a hint. The multiplication table has a diagonal of symmetry. 1 1 makes 1, 2 2's make 4, 3 3's make 9, 4 4's make 16, 5 5's make 25, 6 6's make 36, 7 7's make 49, 8 8's make 64, 9 9's make 81, and 10 10's make 100. This diagonal divides the multiplication table into two parts that are the same. 2, 2, 3, 3, 6, 6, 4, 4, 8, 8, 12, 12, and so on down to 90, 90. Pause the video to take a closer look at the symmetry of the multiplication table and see if you can discover any new patterns. One thing I hope you noticed is that the multiples of each digit can be found two ways. When we counted the multiples of 1, we put them in the first column of multiples. But when we counted the multiples of the other digits, the effect was to also fill in the multiples of 1 in the first row. So we can find the multiples of 1 in the first column of the multiplication table, but we can also find multiples of 1 in the first row of the multiplication table. And the same is true for the multiples of 2, the multiples of 3, and all of the other multiples in the multiplication table. The reason for this pattern is that multiplication is commutative. Multiplication, like addition, has the commutative property. First, we have 1 times 1 on the diagonal of symmetry. Then 2 times 1 is the same as 1 times 2. 3 times 1 is the same as 1 times 3. 4 times 1 is the same as 1 times 4. 5 times 1 is the same as 1 times 5. 6 times 1 is the same as 1 times 6. 7 times 1 is the same as 1 times 7. 8 times 1 is the same as 1 times 8. 9 times 1 is the same as 1 times 9. And 10 times 1 is the same as 1 times 10. The word commute means change together, change with. And multiplication commutes because changing the order of factors does not change the product or the result of the multiplication. 2 1s and 1 2 both make 2. 3 1s and 1 3 both make 3. 4 1s and 1 4 both make 4. 5 1s and 1 5 both make 5. 6 1s and 1 6 both make 6. 7 1s and 1 7 both make 7. 8 1s and 1 8 both make 8. 9 1s and 1 9 both make 9. And 10 1s and 1 10 both make 10. Now let's look at a factor of 2. 2 times 1 is the same as 1 times 2. 2 times 2 is on the diagonal of symmetry. 3 times 2 is the same as 2 times 3. 4 times 2 is the same as 2 times 4. 5 times 2 is the same as 2 times 5. 6 times 2 is the same as 2 times 6. 7 times 2 is the same as 2 times 7. 8 times 2 is the same as 2 times 8. 9 times 2 is the same as 2 times 9. And 10 times 2 is the same as 2 times 10. 1 2 makes 2. and so do 2 1s. 3 2s make 6, and so does 2 3s. 4 2s make 8, and so does 2 4s. 5 2s make 10, and so does 2 5s. 6 2s make 12, and so does 2 6s. 7 2s make 14, and so does 2 7s. 8 2s make 16, and so does 2 8s. 9 2s make 18, and so does 2 9s. 10 2s make 20, and so does 2 10s. Now let's look at a factor of 3. 1 3 makes 3, and so does 3 1s. 2 3s make 6, and so does 3 2s. 3 3s make 9, which is on the diagonal of symmetry. 3 4s make 12, and so does 4 3s. 3 5s make 15, and so does 5 3s. 3 6s make 18, and so does 6 3s. 3 7s make 21, and so does 7 3s. 3 8s make 24, and so does 8 3s. 3 9s make 27, and so does 9 3s. 3 10s make 30, and so does 10 3s. Now let's look at a factor of 4. 1 4 or 4 1s make 4. 2 4s or 4 2s make 8. 3 4s or 4 3s make 12. 4 4s is on the diagonal of symmetry and makes 16. 5 4s or 4 5s make 20. 6 4s or 4 6s make 24. 7 4s or 4 7s make 28. 8 4s or 4 8s make 32. 9 4s or 4 9s make 36. And 10 4s or 4 10s make 40. Now let's look at a factor of 5. 5 1s or 1 5 make 5. 5 2s or 2 5s make 10. 5 3s or 3 5s make 15. 5 4s or 4 5s make 20. 5 5s is on the diagonal of symmetry and make 25. 5 6s or 6 5s make 30. 5 7s or 7 5s make 35. 5 8s or 8 5s make 40. 5 9s or 9 5s make 45. And 5 10s or 10 5s make 50. Now let's look at a factor of 6. Okay, mathematicians, now let's see if you can describe the commutative property for factors of 6. I'm going to give you a minute to look over the table and get your thoughts together, and then we'll start. Are you ready? Let's go. How did you do? Let's check. So it doesn't really matter whether I say, for example, 2 6s or 6 2s make 12, or if I say 6 2s or 2 6s make 12. I can say them in either order. The important thing is I know that this is 2 6s and this is 6 2s. So let me ask you this first column of expressions, 1 times 6, 2 times 6, 3 times 6, 4 times 6, 5 times 6, etc. Are those on the horizontal or the vertical? Are they in the row or are they in the column? I hope you said those expressions are vertical. They're in the column. The second column of expressions, 6 times 1, 6 times 2, 6 times 3, 6 times 4, 6 times 5, etc., those expressions are horizontal. They're in the row. Okay, let's look at a factor of 7. Okay, this one's all you. Are you ready? Let's go. How did you do? Did you remember that the column is 1 7, 2 7s, 3 7s, etc.? And the row is 7 1s, 7 2s, 7 3s, etc.? Why does it matter whether it's 7 5s or 5 7s? If they both make 35, who cares which one is which? Well, there's a very good reason why we do care, and we're going to look at that reason soon. In the meantime, I want you to practice describing the commutative property for factors of 8, 9, and 10. I'll talk to you on the other side of that. Congratulations, mathematicians! You are well on your way to mastering the commutative property and the multiplication table. In the next video, we'll take a deeper look at the commutative property, practice multiplication facts, and learn why order still does matter in multiplication even though it's commutative.